Welcome back. In this video, we'll introduce our next discrete distribution, the Poisson distribution. So the Poisson distribution, we'll start by defining it like we have with the others. We will also discuss some properties of the Poisson distribution. We'll show how to find probabilities related to the Poisson distribution, both by hand and using R. So let's jump in. We say that a random variable y has a Poisson distribution with parameter lambda greater than 0 if the probability that y is equal to y can be found by taking e raised to the negative lambda power times lambda raised to the y divided by y factorial. Now y is discrete integer valued, can take on values beginning at 1, so 0, 1, 2, and to define this we say that y is distributed Poisson with parameter lambda. The Poisson distribution can be used to represent counts, so how many times something occurs over a finite set of time or point area or place in time. For example, we can take a look at how this Poisson distribution changes depending on changing the parameter lambda. For small Poisson lambda, we would expect to see very small counts, things like 0, 1, 2, quite frequently. As we increase our parameter lambda, we start to tend to see higher counts y. So let's take a look at an example. We have data from a hospital maternity ward that suggests that about 4.5 babies are born every day, and the average is 4.5. What's the probability that there will be 6 births on the ward tomorrow? Well, it turns out that that lambda parameter for the Poisson distribution is used to represent the mean over a particular point in time or a particular area in space. So y will be the number of births. Because we know that the average number of births is about 4.5, we'll say that lambda for this distribution is 4.5. So then the probability that y is equal to little y is e to the negative lambda times lambda to the y divided by y factorial. To get the probability that there are 6 births, we'll plug this into our Poisson distribution. We'll get a probability of about 13%. So there's about a 13% chance that there will be 6 births on the ward tomorrow. In order to calculate this in R, we can use either direct calculation. Notice that in order to calculate e to a power, we use the exp function. So exp gives you e to the negative 4.5. The factorial function is simply the word factorial. We can also use those predefined probability functions. Luckily, the Poisson distribution is parameterized the way we think it should be. Let's take a look at another example. According to the U.S. Geological Survey, or the USGS, there have been 36 major earthquakes defined as a 7.0 or more on the Richter scale since 1970. We'll assume that earthquakes are independent. What's the probability that there will be at least one major earthquake in the next year? So we'll let y be the number of earthquakes per year. If we assume that the rate of earthquakes has been unchanged, then that means that 36 earthquakes in a 50-year period, we have an average of about 0.72 per year. So that becomes the lambda in our Poisson distribution. Starting with our Poisson probability mass function, probability of one earthquake in the next year is e to the negative 0.72 times 0.72 raised to the first divided by 1 factorial. There's about a 35% chance of a major earthquake in the next year. So characteristics of this distribution. Assume that y is distributed Poisson lambda, then the expected value of y is in fact lambda. The variance of y for this distribution is lambda squared. So our data suggests that we have about 4.5 babies born every day. Let's find the expected number of births and the standard deviation. So starting with the expected value of a Poisson distribution is just the parameter lambda, so we get 4.5. The standard deviation is the square root of the variance. Now, unfortunately, it looks like there is a typo here in the notes, so I do apologize for that. The variance here of the Poisson distribution should be lambda squared. So the variance is 4.5 squared. The standard deviation should be 4.5. So again, apologies for that mistake on the slide. Let's take a look at another example. So there's been some research on the number of illnesses involving E. coli in Nebraska. We know that sporadic or spontaneous E. coli outbreaks occur at a rate of about 2.4 per 1,000 people over a 2-year period. So that means that in 2 years, out of 100,000 people that are exposed to E. coli, 2.4 of them will get sick. If this rate has not changed and 100,000 are reviewed for this year, what is the probability that at least 5 cases will be observed? So the probability of 5 or more E. coli cases in Nebraska is the probability that y is greater than or equal to 5, which is 1 minus the probability that y is less than 4 because we have a discrete distribution. This should be less than or equal to 4 right here. So then using the p Poisson function, we get 1 minus 0.9. There's about a 9.5% chance roughly of observing 5 or more E. coli cases in Nebraska. So we will stop this video here. Have a great day, and I'll see you in the next one.